Welcome to the AIA Structural Exam Preparation Module number 9. So this will be the last module in this series, and what I'm going to do today is go over some sample problems, just sort of randomly picked from some sample tests, and give you some guidance to hopefully help you with passing these exam problems. So I'm going to select these. I've selected them actually based upon covering different subjects. The first one is a shear moment diagram, and I'm going to draw this out for you, and what the problem statement says is to select the correct shear and moment diagram. So let's draw this out. It's a simply supported beam. With an end reaction here, end reaction here. This is A, B. We have a load here of 8 kips. We have a uniform load. Two kips per foot. Five feet, 5 feet, and 10 feet. Now this problem is a little different from other problems where they're not actually asking you to solve the shear and moment diagram. They're asking you to pick the correct shear and moment diagram. So they actually give you 4 choices. I'm going to draw out those 4 choices. Actually, they're not shear and moment diagrams, they're shear diagrams. So let's look at the 4 choices, and then I want to help you with making a judgment call on which is the correct one. So in this case, it's only the shear diagram. In some cases, they actually will give you the moment diagram, but in this case, it's only the shear diagram. I'm going to use some different colors for each option so that we're clear. So the first option, which is labeled A, looks like this. Comes across this way, drops down. They have values on here also. They have, this is 17 kips, 9 kips, minus 11. So that's your option A. Then option B, I'll draw that one in blue. Option B looks like this. 11 kips, 3 kips, minus 17 kips. That's your option B. Your option C, I'll do that with orange. Option C, 14 kips, goes constant across, drops down, goes across, 6 kips, drops down, minus 14 kips. That's your option C. Option D, I'll use red. Starts off at 14 kips, goes across, drops down, 6 kips, drops linearly to minus 14 kips. So you have 4 options, and we have to decide which one is the correct option. So right away, we can pick one of these as being completely incorrect. Let's do that first, because we're all about eliminating the wrong choices first. And immediately when you look at these 3 options, there's one that doesn't make any sense. And because you have this uniform load, remember that the uniform load causes a slant shear diagram. That comes back from the previous course in one of the earlier modules. Let's just quickly refresh our understanding so that you're clear on that. Remember that when you have a uniform load, simply supported beam, I'm going to number my sheets here. Sheet number 1, module number 9. Sheet number 2. So remember, we've solved this problem in our previous class, and the shear diagram looks like this. The moment diagram is a parabola. So whenever you see a uniform load, you know that you have a linearly varying shear diagram. So which one of these, option A, B, and C, option A, B, C, and D is incorrect? We know that C, which does not have that, that's definitely out. So we can delete option C. We're now down to A, B, and D. So the next step, in order to figure out which one of these is correct, is to calculate the reaction. And the reaction is not really too hard to do, because you can use a shortcut that I taught you in one of the previous lessons. Let's use that shortcut. We can calculate the A reaction. So using this, let's calculate that A reaction. I'm going to fold sheet number 2 so that I can look at both of them at the same time. So the A reaction is going to equal 8 kips times the span ratios. Remember I showed you how to do that before, which is 15 over 20. That's the distance to the right-hand span over the total span. The total span is 20 feet, and the distance to the right-hand reaction is 15. Plus this total load, which can be approximated as 2 times 10 is 20 kips occurring at the center of that span. So that's 20 kips times the distance to the right hand from the center, which is 5 over 20. So that's 8 times 3/4 plus 20 times 1/4, which is 4 goes into that 2, so that's 6 kips, plus 4 goes into that 5, plus 5 is 11 kips. So with that simple calculation, straightforward one-line calculation, we have the left reaction as 11 kips. The right reaction will equal the total load, because we know that A plus B should equal the total load, which is 8 plus, and we calculated that to be 20, should equal 28. So the right reaction is 28 kips minus 11 kips, which is equal to 17 kips. So now we have the right reaction and the left reaction. Now we can solve the problem. If the right reaction is 17 and the left reaction is 11, here they've got it backwards in option A. Option B has got it right, and option C has both reactions as being equal. So we know that option D, this is option D. We know that option D is out, and we know that option A is out. And so the correct answer is option B. And you didn't have to draw the shear and moment diagram. You didn't have to do anything. You just had to do one line of calculation. You were able to eliminate all the 3 options. There's a lot of questions like that on the AIA exam, where you don't have to actually solve it, but just by using a little bit of judgment, you can get to the right answer. Let's go on to the next one. I'll label this as sheet 3. This is a question out of one of the exams. The question is, what are the most frequently used steel rolled beam shapes? And then they give you 4 options. Option A, structural T's. B, angles and L shapes. C, W shapes. D, M shapes. So this is one of those questions you either know or you don't know. So let's talk about it a little bit, give you a little bit of background. Multiple choice, this one should be one of your category A problems that you should be able to solve very quickly. Let's label sheet number 4. So the first one is they're telling you structural T's. Well, what is a structural T? A structural T is a shape that looks like this. And where do we use structural T's? Well, structural T's will be used in bracing elements. They can be used in certain types of maybe joist construction, but they're not very commonly used because it's an unsymmetrical member. It's unsymmetrical, and so it has minimal use to it. Angles and shapes falls into the same category. Angles and L shapes are essentially the same thing. They could be equal leg angles or they could be unequal leg angles. So that's your option B. W shapes are your classic I-beams, where you have your flange and your web. These are symmetrical shapes. These are used as beam elements. They're also used as column elements. And the last one, M shapes, is again an oddball shape, not used very frequently. M shapes are channel shapes. Again, unsymmetrical. So this is an unsymmetrical shape, this is an unsymmetrical shape, unsymmetrical, and unsymmetrical. The answer is C, because W shapes, being symmetrical, are used for beams and columns. All these other ones are sort of oddball shapes. It's a straightforward question. Okay, let's try another problem. This is a more analytical problem. Sheet number 5. This is a steel beam with a span of 18 feet, simply supported, carrying a dead load of 1.5 kips per foot, carrying a live load of 4 kips per foot. Uniform load distribution. And the beam material is made of A992 steel, A992 steel with a yield stress of 50 KSI. So what does the beam look like? Well, it's pretty simple. It's simply supported, so I'll draw it anyway, although you should understand what that is, but let's draw a sketch. So we have a uniform load, and our W, dead load plus live load. Simply supported beams have a straightforward calculation. You should remember this. The moment is WL squared over 8. The shear is WL over 2. You shouldn't have to look that up. You should remember that. So they're asking for, here's the question. They want to know, what is the minimum plastic section modulus? What is the minimum plastic section modulus? So let's do a little review on what that is. Remember, when we talked about steel in the previous module, that steel has a stress-strain curve. The stress-strain curve has a yield point, and then it goes into the plastic zone. So at this yield point, this stress-strain curve is divided into 2 zones. We have the zone on the left, which is the linear elastic zone. And then we have the plastic zone. The plastic zone is where the material becomes deformed permanently. The linear elastic zone is the zone where the material will go back to its original condition. This point here defines the defining point between the linear elastic zone, which I'll label in red, and the plastic zone, which I'll label in blue. And so the plastic section modulus which is commonly referred to as Z, refers to that yield stress. And so if we calculate the stress in a beam as M over S, we replace the S. S is an elastic section modulus. That's to keep us in the elastic zone. We replace that with Z. And so we're trying to calculate Z, and FB will become the yield stress. So this becomes our equation. And so the plastic section modulus becomes the moment divided by the yield stress. And so in order to calculate that, we need to calculate the moment. We already have the yield stress, but we have to calculate this based upon factored loads. So let's do that. We'll go back to the problem statement, and we're going to calculate this based on factored loads. So there's two ways to solve this problem. We'll do it both ways. One is using the LRFD method, and the other way is using the allowable stress design method. Let's do the LRFD method first. LRFD method, we have to use factored loads. Factored loads for LRFD is our ultimate load is going to be 1.2 times the dead load plus 1.6 times the live load. These load factors come from the code books. So our ultimate load is 1.2 times the dead load. What was the dead load? The dead load was 1.5 kips per foot, and the live load was 4 kips per foot. So 1.2 times 1.5 plus 1.6 times 4. Let's do the math on that. That comes out to be 1.2 times 1.5 is 1.875. And this is 1.6 times 4 is 6.4. We add those two, and we get 8.275, which will approximate to 8.3 kips per foot. Now we can calculate our ultimate bending moment using the ultimate load, which will be W ultimate L squared over 8. And so that becomes 8.3 times the span, which was 18 feet. So times 18 squared divided by 8. So let's see what that is. 8.3 times 18 squared divided by 8. 336.15 foot kips. We're going to convert that unit-wise because our yield strength is in KSI. We have to watch the units. So we're going to convert that into inch kips. So that converts into inch kips, 336 multiplied by 12. 4,033.8 inch kips. That's our ultimate moment. That's the moment that we're going to plug into this formula for the section modulus. And so if we do that, going over to sheet number 8, our section modulus, plastic section modulus, is going to be our ultimate moment divided by, and we're going to insert the phi factor into the yield stress. I'll explain what that phi factor is in a moment because that's sort of like a little factor of safety. So Z is going to become 4,033.8 inch kips divided by, in this case, the phi factor is 0.9 times 50 KSI. We have consistent units, kip per inches squared, so Z will come out in inches cubed because these units will cancel. And so let's see what that number is. 4,033.8 divided by 0.9 times 50 gives us 89.64 inches cubed. And this is a multiple choice test, so you'll see that one of the answers, the actual answer on this that they give you is 89, so that would be the one that you would select. Now, where did that phi factor come from? Well, that's again another factor of safety. Going back to the stress strain curve, we don't like to be right at the yield, so we put in a 10% margin. So we use a phi factor, and it varies whether or not it's for bending stress or shear stress, but for bending, we use a phi factor of 0.9. Just another little factor of safety. We don't want to be exactly at the yield point, we want to be just close to it. That's our answer at 89. Let's do the same problem over again. This time let's use ASD, allowable stress design. Solve the same problem over again. Let's do that. So, sheet number 9, same problem, ASD. In ASD, we work with the service load. The service load is the dead load plus the live load. We put the factors on later, so we have 1.5 plus 4 equals 5.5 kip per foot. We calculate the maximum service moment, same equation, WL squared over 8, except that now we're using the unfactored loads. So that's 5.5 times 18 squared over 8. Let's see what that comes out to be. 5.5 times 18 squared divided by 8. 222.75, we'll approximate that to 222.8. Foot kips, we have to convert the units. So we convert that, multiply by 12. We get 2673 inch kips. And the Z is going to be the service load moment times the omega factor, which is the overstrength factor divided by the yield strength. This has all of the load factors that we talked about earlier buried into that, and that overstrength factor multiplied by the moment, 2673, 1.67 is our overstrength factor divided by 50, which will give us our Z. So let's do that. That's 2673 times 1.67 divided by 50 gives us 89.27. Not exactly the same answer, but reasonably close. Gives us the same solution, which is Z is 89. Let's go on to the next one. We'll do one more. This one is a W18 by 46 steel member with a yield stress 50 KSI, simply supported with a span of 18 feet. Supports a dead load of 1.8 kip per foot and a live load of 3 kips per foot. And I'll give you some of the values on this member. For a W18 by 46 member, the depth of the member is 18.1 inches. The web thickness is 0.36 inches. And the H depth to thickness ratio is 44.6. The modulus of elasticity is 29,000 KSI. And they're asking for the shear strength. what is the shear strength? So in order to calculate the shear strength, let's understand a little bit about a steel beam, first of all, and get a little background on that. Steel beams, W shapes, transfer shear primarily through one element. When I put a load on this, the flanges, I'm going to use a couple different colors here. The flanges are primarily for bending. And the reason is because the moment of inertia, which is AD squared, the A is coming from this area times the distance D to the neutral axis. So this is primarily for bending. That's because that's where you get your primary moment of inertia. For shear, it's primarily the web. It's the web that takes the majority of the shear, because the load transfers in here, goes right into this member. The flange really isn't doing anything for you in terms of shear. So the shear is taken by this distance, this area, which is h times the thickness of the web. This is my thickness of my web, and h is the height of the member. And so the shear stress distribution on a wide flange section, which you can calculate or derive, the shear stress distribution looks like this. I'm going to go ahead and draw it on the same sketch here using orange. It is a parabolic distribution, the highest stress occurring right at the center, at the neutral axis. Unlike bending, where the bending stress has a different distribution. Remember that the bending stress is 0. That's your bending stress. That's your shear stress. So now, in order to solve the problem, what is the shear strength? Let's go back to AISC, which gives us the nominal shear strength for a section as 0.6 Fy, area of the web, times modification factor CV. Our yield strength is 50 KSI. Our area of the web, which is the depth times the thickness of the web, is going to be 18.1 times the thickness of the web, 0.36 square inches, which works out to 18.1 times 0.36 is 6 point, and I'll round it off, 6.52 square inches. That's our area of our web. And the web shear coefficient, CV, is calculated based upon the H height to thickness ratio. There is a straightforward formula in the steel code that relates the height to thickness ratio. If it's less than 2.24 square root E over Fy, then the shear ratio is 1. So we got to calculate what this ratio, what this coefficient is. So 2.24 square root 29,000 divided by 50. You got to keep your units straight. This number calculates 2. Let's do that. 29,000 divided by 50. Take the square root times 2.24 is 53.95. So that's our limit. And in this case, our depth to thickness ratio, I'm using H and D kind of interchangeably, but they're the same thing, is 44.6. So 44.6 sheet number 12. Our height to thickness ratio, 44.6, is less than 53.95. Therefore, our shear coefficient is 1. So the nominal shear capacity is 0.6 Fy times the area of the web times 1. That works out to 0.6 times 50 times the area of the web, 6.52 times 1. And that works out to 0.6 times 50 times 6.52, 195.6 kips. Now remember, that's a nominal shear capacity. And because our phi factor for shear, the design shear strength is 1, then our design shear capacity is the same in this case. The allowable shear strength using working stress design is going to be, so this will be our allowable, which will be our nominal divided by the omega reduction factor for shear, will be 195.6 divided by 1.5. That's the omega reduction factor. That works out to 130.4 kips. Allowable and ultimate. Let's try one more. Sheet number 13. This is a column in a 7-story building. Located on a square grid, 20 feet by 20 feet, with service loads, dead load service load of 90 pounds per square feet, 90 PSF, and a live load of 50 PSF, which includes all of the self weights. So that's everything. That's dead load and live load. It includes the self weight of the floor. And so it's asking for what is the typical first floor interior column load. So let's do the calculation for that. Now, according to ACI, so let's first understand the problem. Okay, so what we have is you have a floor system where you have a series of columns which are separated out on a 20-foot by 20-foot grid. That means that the spacing column to column is 20 feet. And we don't need to know the entire dimension of the floor. What they've told us is that the grid is 20 by 20, which tells us that the tributary area load that means that for one column, my tributary area load because my spacing to my next column is 20 feet, my tributary area load is going to be half of that, 10 feet plus the 10 feet to the other column. So my tributary area load is going to be 20 feet by 20 feet. It's the spacing in between each column divided by 2, but then you add it to the other column, and so I end up with an equal grid. 10, 10, 10, 10. And so that tributary area load is 400 square feet. And that is added times each floor level up above. In this case, they're asking for the load on the first floor column. So according to ACI, we have to use ultimate loads So let's calculate what that ultimate load is. 1.2 times the dead load plus 1.6 times the live load. 1.2 times the dead load, our dead load is 90, plus 1.6. 90 is our dead load, 50 is our live load. 1.6 times 50. And so the answer is, let's multiply that out, 1.2 times 50 plus 1.6, excuse me, I did not do that correctly, let's try that again. 1.2 times 90 plus 1.6 times 50. 1.2 times 90 plus 1.6 times 50. And the answer is 188. PSF ultimate load. And so the column load is 188 PSF times the tributary area, which is 400 square feet, because as we discussed earlier, that tributary area is based upon that equal grid spacing. So 188 PSF times 400 square feet, this is my ultimate column load, and that works out to be 188 times 400, which is 75,200 pounds. That's per floor. And how many floors do we have? We have 7 floors. So on the first floor column, because now let's just do a quick sketch. Here's my building, and I'll make this rather simple. One, 2, 3, 4, 5, 6. I'm going to add one more. 7 floors. My column down here, I have to add each one of these loads in order to get down to the first floor column. So my first floor load is going to be 7 times 75,200. And the answer is 526,400 pounds, or roughly 526.4 kips, which we can round up to 530 kips. 530 kips is about 500,000 pounds on one column. So I hope that helps you out, and I may be adding more modules to this series, but I think that you have now 9 modules to work with, and I hope that's useful to you. And I want to wish you good luck on your test, and stay in touch with me and let me know that you pass. And hopefully we'll be adding some more to this in the near future. But I wish you good luck. Don't study too hard, but make sure you pass your exam and then go and celebrate and have a party. Thank you so much.